Today we're going to be looking at something called the photoelectric effect, and this was a concept that is very key in proving the existence of photons. Now this may be quite a confusing topic to just start off with, so I'm going to start off with a little analogy. So let's say you're stuck in this hole here, and this hole is of some height, and we know that the gravitational potential energy required to get out of this hole is equal to mgh. So let's say the gravitational potential energy was, let's say 1000 joules. You needed 1000 joules to get out of this hole. And you and your body currently, you have exactly 0 joules. And obviously, that's not realistic, but let's just say in the case you have zero energy to use to jump out this hole. And now this helicopter flying above is carrying food, and it drops you 10 joules of food. Now here you are, and you consume that 10 joules, so now you have 10 joules of energy. And what you try to do is you try to jump. Are you going to get out of that hole? Well, clearly not, because you need 1000 joules to get out of this hole, and you've only eaten 10 joules. So you're going to jump up to here maybe, and then you're just going to fall back down. And once you've tried to jump out, after eating those 10 joules, you now have 0 joules of energy again. This time, the helicopter flies by and gives you 500 joules. And the same thing's actually going to happen. You're going to consume this 500 joules of energy, you're going to try to jump out, you're going to realize it's not enough, and you're going to fall back down, and you're going to end up with 0 joules again. Now, if this helicopter supplies you exactly 1000 joules, you now consume all those 1000 joules and you jump up. And at this point, you just about have enough energy to just about make it out of the hole, which means that you jump up and you exit this hole with 0 kinetic energy. So you're able to jump out the hole and maybe you can reach this cliff here, but you don't have energy to move after that. So let's say this time round the helicopter supplies you with 1100 joules of food. So you consume all of that, try to jump out, you manage to jump out, and you can now walk away with 100 joules of kinetic energy. Now this is basically what the photoelectric effect is. Instead of you being stuck in a hole, it's an electron being stuck inside a metal. And instead of supplying it food, you're supplying it photon energies. And once you reach a certain designated energy level, the electrons are now allowed to escape from the metal. Now we know one of the properties of metals is that they have delocalized electrons. Electrons that are just free to move. And here I have this photon generator that will emit photons that will hit the surface. And what I can do is I can change the frequency on this generator. And we know that because E is equal to HF. If I change the frequency, I'm going to end up changing the energy of these photons. Now in the previous case, we said that we needed 1000 joules to jump out of that hole. Let's say that we now need 100 joules for an electron to be released from the surface. So if I end up supplying 50 joules of energy from a photon, when this interacts with one of the electrons, that electron is going to absorb all that 50 joules of energy, try to release, realize it cannot release, and just stay inside the surface. So if I'm supplying 50 joules of photon energy, no photons are going to be released. If I now supply 100 joules of energy via photons onto the surface, the electrons will be able to be just released. And we know that they will absorb all this 100 joules of energy each and be released and have a kinetic energy of 0. If I now supply 300 joules of photon energy, not only are these electrons in the surface going to get released, but they are also going to get released with a kinetic energy of 200 joules. If we start off with a relatively low photon energy and we increase this photon energy, we're going to start seeing that initially there'll be no electrons released from this surface. But as we keep increasing and increasing, the electrons will start to get released with more and more kinetic energy. Now there are a couple definitions that we need to go over. First is something called the work function. Now in this case, the work function of this metal is 100 joules. What it means is the energy of photons required so that the electrons get just released with 0 kinetic energy. In other words, it is the minimum energy required to liberate an electron. So in this case here, we needed 100 joules of energy to just about liberate one of the electrons. The other is something called the threshold frequency. And we know that because E is equal to HF, At the specific designated work function, which I'm going to denote by this psi here, it's a Greek letter, we can say that there has to be some minimum frequency as well. So therefore, the threshold frequency is the minimum frequency required to liberate an electron. So the work function is the minimum energy of a photon required to liberate an electron, whereas the threshold frequency is the minimum frequency required to liberate an electron. So let's see what that means in this case here. Well, if I started off with an energy less than the work function, there will be no liberation. None of the electrons will get released. And if you had an ammeter connected, you won't see any current. In the second scenario, if my photon energy was equal to the work function, or in other words, if the frequency of the photons was equal to the threshold frequency, the electrons will get liberated with zero kinetic energy. And in the third case, if I had a greater photon energy than work function, the electrons will get liberated with some kinetic energy. And we could therefore say that the kinetic energy of these electrons is equal to the energy supplied by the photons minus the work function of that metal. So what I can do is I can actually play around with this equation. Well, we know that E is equal to HF, so I could rewrite this as the kinetic energy is equal to HF minus the work function. So if I was carrying out some data or doing an experiment, and I could determine the kinetic energies of these electrons released, and the frequency of the photons emitted by the generator was known, we could then plot a graph of kinetic energy on the y-axis against the photon frequency. And we can just do simple analysis to see that the gradient of this graph is going to be given by Planck's constant, and the y-intercept of this graph is going to be the negative of the work function. So you're going to see a graph that looks something like that, where this value here is minus the work function, and the gradient of this graph is equal to Planck's constant. So let's say this graph here was if the work function was 100 joules. Well, what does it mean now if I change my metal and let's say the new metal had a work function of 300 joules? Now all I'm changing is the work function, so the only thing that will change in this graph is the y-intercept. And because the magnitude of the work function is increasing, this value here will be more negative. So you're going to see a graph that looks something like that. And notice it will have the exact same gradient as the other one, because Planck's constant is a constant. Now you might be thinking, well, what if the work function of a metal was 100 joules, and I supplied 50 joules of photon energy? Why can't an electron just take two photons and absorb two photons, and then it will have 100 joules and then it can just get released? Well, it doesn't quite work like that. See, photons and electrons have a one-to-one relationship. And what that means is one electron must consume the energy of one photon and expend it before consuming the energy of another. So what that means is the electron has to absorb the energy of one photon, try and get out, realize it can't, and then absorb another. It cannot just accumulate lots of energies from all different photons. It doesn't work like that. Now, if you were to somehow do this experiment in real life, you'd actually notice that the kinetic energy of electrons released will vary. And why is that the case? Well, if you look at a metal, there are lots of electrons on the surface of this metal, but there are also electrons that are further down, deeper in the metal. So for any electrons that are deeper in the metal, the work function will increase. And that means it will require more energy for these electrons to get released. So ensuring we keep the photon energy the same, So we're keeping the photon energy as it is. If the work function varies for different depths within the metal, since kinetic energy is equal to the energy of this photon minus the work function, we can clearly see that the kinetic energy will vary if the work function is changing. So if the kinetic energy is varying, then you'll see that the speeds of electrons released will vary as well. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.